Hello everyone. In the last video, we talked about the solution near ordinary point. In this video, we're going to talk about the solution near singular point. Okay, for the second ODE. The general form, as we already talked, for the second ODE is in this form, which is d square y over dx square plus p, a function of x, p1 time dy over dx plus p2, a function of x time y equal to 0, and p1, which is q over p. Both functions are function of x. Okay, and p2 is rx over px. Both functions are function of x. Okay, for the solution near singular point, there are two types. The first one is regular singular point, which we can talk in this video today. And the second one is irregular singular point, which is more complicated, and we're not going to talk about this in this class. Okay. And for this, we have to check if when we have singular point, which we have to check if it's regular singular point or irregular singular point. How are we gonna check? Okay, we have to follow these two steps. Okay, the first step is to check the limit of a function of x minus x0. X0 is the point that we pick, time p1, p1 x, which is the p1 is function of x, right? And you find the value of this answer. Okay, and then we also check the limit of x minus x0. Both of these in this parenthesis square times p2x equal to something. And if we can find these answers, or we can find the value of these a and b, then it's gonna be regular singular point. Okay, in other case it's gonna be irregular singular point. Okay, let's check an example. Okay, as I said in the previous slide, if we can find a solution for both a and b, then that point, the x0, this is a regular singular point. But if we cannot find the solution of a or b or both, then it's going to be irregular singular point. Okay, and again, we're going to talk only about the regular singular point. Okay, let's see these examples. Okay, we have x times x minus 1 in this parenthesis to the third times y double prime plus 2 in this parenthesis x minus 1 to the third times y prime plus 3y equal to 0. Okay, first you have to rearrange to get y double prime plus p1 y prime plus p2 y, right, equal to 0. And then you find the limit of a and b function. Okay, as here is p is the x times x minus 1 to the third. Okay, so p1 is here 2 times x minus 1 to the third over x, which is p, right, x times x minus 1 to the third. Okay, and then you can reduce the form to get 2 over x, and also p2 is this one, 3, right? It's 3 over p. P is x times x minus 1 to the third, so this is p2 and this is p1. Then you find the limit of p1 and p2. Okay, after you get p1 and p2 function, then you have to check what the value that makes this term go to 0, which is the p1 term, p function term, which is x times x minus 1 here to the third, and also this is also p, which is x times, in this parenthesis, x minus 1 to the third. When you think about this, the value that makes this term, this form, go to 0, which is x equal to 0 and also x equal to 1, right? So the two values, which is 0 and 1, that makes the function, this function, go to the going to be the singular point, right? So we have to check one by one value. At x0 equal to 0, then we have to check the limit of this one, x equal to x minus x0, which is 0, x minus 0, okay, times 2 over x, which is p1, right? So x, we cross it out, so the answer is 2. And when we check the limit of the b form, which is the limit of x minus x0, which is x0 is equal to 0 square, right, times p2. p2 is 3 over x times x minus 1 here to the third. We can reduce the form and then we get 3x, right, x here times 3, so we get 3x over we have x squared, right, so we cross out 1 of it, we get x 3x over x minus 1 to the third. Okay, when we replace x with 0 here, so we're gonna get what is it, 3 times 0 is 0, and 0 minus 1 is minus 1 to the third, so 0 over something equal to 0. So we can find the value of a and b. So this is a regular singular point. Okay, and again we have to check when x0 equal to 1, right, because the value of 1 also the singular point. Okay, in the case A, check the limit of x minus x0, which is 1, times p1, which is 2 over x equal to 0 when x approaching to 1 in this case. And we got it, what is it, when we replace this 1 minus 1 equals to 0, 0 times something equals to 0. And in the case B, we check the limit of x minus x0, which is 1 square, times p1, p2, sorry, p2, this is p2, and we can reduce the form, okay, 3 over x times x minus 1, and check and replace x with 1, so 1 minus 1 equal to 0, and 0 times 1 is also 0, so 3 over 0 is going to be like, it's not really 0, but this is because x approaching to 1, so it's very close to 1. So this is 3 over very small value, so it's gonna be go to infinity. So when x 0 equal to 1, it's gonna be irregular singular point. That's because we cannot find the value of the second case, the B case. Okay, this is how we check is regular singular point or irregular singular point. Okay, this slide shows another example. Here we have x squared minus 1 times y double prime plus, in this parenthesis, x plus 1 times y equal to 0. And when you think about this a problem, here we have px function, which is x squared minus 1, we don't have P1 since y prime equal to 0, the y prime function. So P1 x is equal to 0, and P2 is x plus 1 over P, Px, which is x squared minus 1. So when we think about it, think about the Px function, the value that makes this term go to 0, which is plus 1 and minus 1. So the value that makes this problem going to be the singular point is plus 1 and minus 1. Now we have to check the plus 1 and minus 1 is going to be irregular singular point or regular singular point. Okay, so in the case, so we just check one by one. Now we have to check at x0 equal to plus 1 first. In the case A, we don't need to find it since the P1 equal to 0, so it's going to be 0 in the case A. So case B, the limit of x approaching to 1 of this function, which is x minus x0 is x minus 1 square, right, square here, times P2. P2 is x plus 1 over x squared minus 1. So when we can reduce the form, we get here, which is we reduce the form, we get in this one we can get x plus 1, x minus 1. So we cross 1 out, so we get x minus 1. Okay, so think about it. There's plus sign here, right? We cross 1 out, and x minus 1, we cross 1 out here, so we have x minus 1 left. Okay, x minus 1 left. So when we replace with 1 in this limit, 1 minus 1 is 0. So we got, in the case A we got 0, case B we got 0. So this is regular singular point for x0 equal to plus 1. Okay, so next is check at x0 equal to minus 1. Okay, minus 1. So the case A we don't need to find it again because it's equal to 0, and case B, check the limit of when x approaching to minus 1. So x minus minus is plus sign, x plus 1 square times P2 is x plus 1 over x minus 1. Again, we can reduce the form, we get x plus 1 square over x minus 1. Okay, and then when we replace this minus 1, right, minus 1 plus 1 is 0, and this is minus 1 minus 1 is minus 2, so 0 times minus 2 is 0. So this is also going to be regular singular point for the case x equal to minus 1 in this case. So both value plus 1 and minus 1, they are regular singular point in this case. Okay, now I'm going to show you how to find the solution near the regular singular point. Okay, and to answer the second ODE in terms of series solution using the regular singular point, we have to use the Frobenius method. Okay, the general form of the solution for the Frobenius method is going to be in this term, which is y equal to the summation of Cn times x minus x0 to n plus r, and n starting from 0 to infinity. Okay, when you write down n equal to 0, it should be under the symbol of the summation, and in infinity it should be above the summation form. Okay, and in this case r and cn is a constant and c0 is not equal to 0, and r is a solution of initial equation that we have learned from the previous slide, our previous video. Okay, and in this case r has two roots, okay, which is r1 and r2, and when you assign r1, it has to be equal to r or larger or greater than r2, and r1 and r2, they are real numbers. Okay, and the general form of the Frobenius solution is going to be y equal to a times y1 plus b y2. Okay, y1 is from the root of r1 and y2 is from the root of r2. So for the solution here, in the case of Frobenius method, there are three cases. Okay, for the case 1, when r1 minus r2 is not a member of positive integer. Okay, it's not a positive, it's not a member of positive integer. So the solution is gonna be this one, which is y1, y2. y1 is equal to, in the absolute of x minus x0 to the r1, which is power r1, times the summation of cn x minus x0 in this parenthesis to the n, and again c0 is not equal to 0, and y2 is similar. This is x minus x0 power r2 absolute, in this absolute, times the summation of dn. Okay, dn times x minus xs, sorry, this is x0, this is x0 to the n, and d0 is not equal to 0, and both cases is n starting from 0 to the infinity. So that means r1 minus r2 is not going to be, it can be a negative value. Okay, but it's not negative, but it's also not a positive integer. Okay, and this case 1 we're going to learn in this class only. For the case 2 and 3 we're not going to learn in this class. Okay, for the case 2 and case 3 is shown in this slide, but I just show you the general form of the answer, but we're not going to learn in this class, which is case 2 is r1 minus r2 is a member of positive integer. Okay, which is gonna be x minus x0 power r1 times the summation of cn times x minus x0 in this parenthesis to the n, and cn c0 is equal to 0, and y2 equal to x2 minus x0 to the r times the summation of dn times x minus x0 to the n plus c, a constant, y1 of a function of x times ln x, the absolute ln x, and d0 is equal to 0. And the case number 3 is r1 minus r2 equal to 0, or r1 equal to r2. Then solution is going to be in this form, which is y1 y1 is equal to x minus x0 power r times the summation of cn times x minus x0 power n to the n, and c0 is not equal to 0, and y2 equal to x minus x0 to the r times the summation of dn x minus x0 to the n plus r1, sorry, y1 of the function of x times ln x, and the n is not equal to 0. So this is more complicated than the case 1. As I said, in this class we're gonna learn only the case 1 only, which is the most easier one. Okay. Now take a look at example of using Frobenius method to solve the solution for the second ODE in terms of series solutions. To answer the second ODE problem in terms of series solution using the Frobenius method, we have to find the form of limit a and b as I said before, and both a and b has to be regular singular points so we can find the answer. And as I said, in the three cases, we're gonna learn only case A only. So let's take a look in detail. Okay, here we have 2x squared times y double prime minus x times, in this parenthesis, x minus 1 times y prime minus y equal to 0. And of course, if we want to use the Frobenius method, it has to be singular point, right? So for the singular point, we look at the px term here, which is x equal to 0. It's going to be a singular point, right? X equal to 0 is going to be singular point, but we have to check if it is regular singular point. So we have to check the limit of case A and case B. So from here we can rearrange to get P1 and P2. For the case of P1, you just rearrange it, you get this minus x, in this parenthesis x minus 1 over 2x squared, right? In this form we get minus, in this parenthesis, x minus 1 over 2x. Okay, and for the P2 is minus 1 here, so minus 1 over 2x squared, which is equal to P2. So now you have to check case by case. For the case A, we check the limit of this function approaching x approaching to 0, which is P1, which is minus in this parenthesis x minus 1 over 2x times x minus x0 equal to 0. So it's a little confusing here because I switch x0 and x minus 1. So but it's the same meaning. So it's gonna be P1, which is x minus 1 here, there's minus sign here, and x minus x0 is x0, x minus 0 here, over 2x, right? And then we can reduce the form. We get minus x minus 2 or minus 1 over 2. So when we replace with 0, this is, we get plus sign, so plus 1 over 2. Now we got an answer. Okay, for the case B, take the limit of P2, which is minus 1 over 2x squared, minus 1, minus the minus sign here, and 1 over 2x squared, and x minus x0, which is 0 squared, right? So we can reduce the form, we get minus 1 over 2. So whatever, when they replace with 0, substitute with 0, we're gonna get minus 1 over 2. So for the both cases, we get answers which is 1 over 2 and minus 1 over 2. So this is gonna be regular singular point. Okay, now you can use the Frobenius method to solve the the problem to get the answer. So for x equal to 0, when we write down the general form, it's going to be like this. This is y equal to the summation of Cn x minus x0, x0 equal to 0. So we don't need to write down. Just write x and power n plus r, starting n equal to 0 to infinity. We do the same thing with the ordinary point, which is do the first derivative of the general form of this y function. Okay, when we do the first derivative, we get Cn times n plus r times x to the n plus r minus 1 from here, right? N starting from 0 to infinity. In this case, we have to write down n starting from 0 because sometimes when we replace with 0, there's a value. But for the ordinary point, when we do the first derivative, we don't need to write n equal to 0 when we have to use n equal to 1. Because when we do when we substitute n equal to 0 for the ordinary point, there's no value which is equal to 0, so we don't need to write down n equal to 0. But for the Frobenius method, we have to write down n starting from 0. Okay, and again for the second derivative of this y here, we get n plus r times n plus r minus 1 times Cn times x to the n plus r minus 2, and again of this Cn, so C0 is not equal to 0. Okay, then we do the same thing. We substitute y prime and y double prime into this problem. Okay, and we solve the problem. And next, you substitute y double prime, y prime, and y into the problem. Okay, and then you rearrange the form. From here we have x squared, right? So you can multiply x squared into x here, x to the n plus r minus 2. So it's going to be x to the n plus r minus 2 plus 2. The plus 2 here. We're going to get 2 here, the same, and x to the n plus r. Okay. And this form is you multiply x, minus x squared, right? This x minus x squared here. You're gonna get plus 1. I'm gonna talk so much in detail. You have to think about it. And also minus, that's minus is plus side. This plus x into here. You distribute this form. Okay, so we get this form, which is x to the n plus r for the second form, which is this one. And this form is the same, right? Okay, next is you can reduce the form whatever you like, but here I reduce this form. When we have the same power, this is n plus r, n plus r, n plus r, you can reduce into the same form. But in this case, I reduce this form and this form into n plus r minus 1. And the first form the same, second form the same. And in the next step, you have to adjust the value of x to the n plus something to be the same value. So in this case, I adjust x to the n plus r for every term. In the first term, is the same because x to the n plus r, right? So just take it down here. For the second term, if you look at the previous slide, in this one, it's gonna, we adjust from x to the n plus r plus 1. Now we have to reduce to the n plus r, right? So in this case, you have to minus 1 for in this summation form. So n is going to be n minus 1, and n plus r is going to be n plus r minus 1, right? And x to the n plus r plus 1, so minus 1, so it's going to be n plus r. And the summation, the starting from the previous slide, is starting from n equal to 0. So here we subtract 1, right? We reduce one value, subtract 1. So here we have to add up 1. So n starting from 0 is going to be 1 in this case. Okay. And the third form is the same. Just take it out here. Next is you look at the summation. This is n starting from 0, starting from 1, starting from 0. So now you adjust to the highest value, which is n equal to 1. Okay. The first term, when you substitute with n equal to 0, you can get r times r minus 1, right? C0 x to the r, okay, which is this term. And this term is the same, so no need to replace with 0. And this term is starting from 0, so we have to substitute with 0, and we get r minus 1, this one, times c0 times x to the r, which is this form. And the rest we reduce into the same, into one form, which is this is sorry, this is no minus sign. It's the time, the multiply. Okay, it's not minus, it's multiply. So just reduce n plus r times n plus r minus 1, which is this one, times cn minus here is minus cn minus 1 times n plus r minus 1, which is this one, and n plus r minus 1, n plus r minus 1 times cn is here, of this times x to the n plus r. Okay. Now, next step is you have to consider this term only. Okay. Consider this term only. So from here we get 2r times r minus 1 and also r minus 1. So since c0, okay, c0 we consider without x to the r. Okay, just consider this form without x to the r. Okay, since c0 is not equal to 0, so that means this form, which is 2r times r minus 1 plus r minus 1, this is equal to 0. And we can also reduce the form from here into 2r plus 1 times r minus 1. Okay, so that means r equal to minus 1.5 and 1. All right, so the value, we assign the value of r1 to be the highest value, which is 1, and r2 is the lower one, the lower value, which is minus 1.5. Okay, so after that you have to consider the value of r1 minus r2 and think what's the case of this. So the value of r1 is 1, r2 is minus 1.5, so r1 minus r2 is 1 minus 1.5, so it's gonna be 1.5, right? So this answer, which is not a member of positive integer. So in this case, it's case number 1, which is, as I said before, that's this case we're gonna learn in this class. So after that, we pick the solution of case 1, right, from that slide, which is take a look at it. Okay, you have next is you have to find the value of y1 and y2, the general form of y1 and y2. So to get y1, you substitute with r equal to 1 into the star form in the previous slide. Take a look at it. And when we substitute with 1, we're gonna get n plus 1, n plus 1, and n plus 1. Okay, and then we have to find recurrent relation from this. Okay, and here don't forget we have to start from 1, since we already use n equal to 0. Okay, so in starting from 1, okay, take n plus 1 times n. Okay, 2, the 2 here, 2 times n plus 1 times n, cn. Consider without x to the n plus 1. Okay, and this one we get minus n times cn minus 1. Okay, and this one we get n times cn, and we can rearrange the form, and we get cn equal to cn minus 1 over 2n plus 3, and n starting from 1. Okay, don't forget the higher value is on this side. Okay, the lower one, which is cn minus 1, is the lower one, is on the right side. Okay, this is called recurrent relation of R1. Okay, the next step, you find the value of each one, which is n equal to 1, n equal to 2, n equal to 3, and then you find the general form, or you can just write down like this. It's okay. Or this is the general form. This is more difficult, okay, but you need to find it. So the general form of y1 is x from the general form. This is the formula, okay, for the case number 1. Is x minus x0 in the absolute power r1 times the summation of cn times x to x0 to the n, starting n equal to 0 to infinity, and c0 is not equal to 0. So the general form is here, which is, you can just write down like this. So y1 plus x, which is x minus x0, x0 equal to 0. So we have x times the summation form, which is this form, c0 plus c1, c1 is c0 over c5 times x plus blah blah blah. Okay, and this is the general form. Okay, and we get y1. So the next is we have to find y2. To find y2, we have to substitute r2 equal to minus 1.5 into the star. Okay, and do the same thing. I'm not gonna talk in detail. Okay, you reduce the form, you get this term. Okay, recurrent relation term, and the final you get cn equal to cn minus 1 over 2n. Okay, and this one also n starting from 1. This is called recurrent relation of r2 equal to minus 1.5. Okay. Again, you substitute starting from 1, right? This is 2, this is 3, this is 4, 5, until to the n, or to the k here. And also the general form of y2, this is the formula. Okay. And since x equals to 0, x0 equal to 0, so it's going to be x. And don't forget, to the r, the power is r, right? So here is, don't forget, this is the minus sign. That should be minus sign. Okay, minus sign is minus 1.5, minus 1.5, and time this summation form. And the final solution is here. It's y equal to like a constant k1, let's say, time y1 plus k2 time y2, and you get the final answer here. So this is the solution in terms of series solution for the singular point, and in the case of regular singular point and case number 1. So there are like many subsets under the singular point, but in this case we're gonna learn only the regular singular point for the case number 1 only. And here is another solution in the summary. Is another solution that we can get the form or the answer for the second ODE in terms of series solution. Sometimes when you look at the transport phenomena books, you're gonna see the solution of second ODE in terms of series solution, which is how we get the answer. We do like this. Okay, you know how to, now you know how to get the answer. Okay, I will see you in the next chapter, and see you in the class 2. Okay, bye.